अच्छा जी, रिकॉर्डिंग फॉर दिस क्लास. दिस इज DC circuits और इसमें कुछ symbols हैं and those symbols are very familiar in terms of O levels. You already know them, but I will go through a few of them before I get to the question. Okay, so what are we supposed to do in this topic? First, we see point number 1 and 2. We have already done these points in terms of O levels, right? He wants you to understand that what symbols look like and what common symbols in O-level syllabus or A-level syllabus are going to be used. Okay, the third part is to understand the difference between EMF and voltage, right? And potential difference. I will also add the link of one of the O-level IGCSE video concepts, but if you're already familiar with this, you can move on to the next topic. So understand the internal resistance and the EMF and terminal potential difference. We'll get to that later, but first we will get to the part of series and parallel resistances proofs. How to do the proof. Okay, so first we start with the series combination, right? Now in series combination, you will see that resistors will be added one after the other in a single circuit, right? And we call this series because we understand that whatever current will be in this side of the circuit, that will be similar towards this side, and this side. And eventually, of course, it is being originated from the battery and it goes back to the battery. So whatever current is being generated by the battery, the current remains same throughout the circuit, right? And let's assume that the individual resistances of these resistors is R1, R2, and R3, okay? Then we move on to this idea that point number 1, the current remains same. The current is same in series circuit, right? So this leads to the idea that the current generated by the battery, that is IB, is equal to I1, is equal to I2, is equal to I3. Let's call this I1, I2, and I3, and let's call this IB as the current generated by the battery. So the current is going to remain the same, okay? The second point is that voltage divides, or voltage is shared between the resistors. Now voltage is energy, right? Because we know that the formula for voltage is work done by charge. So work done is joules per coulomb. So voltage is primarily the energy of electron. So voltage divides, or you can say it shares between the resistors. So we can say that the voltage of the battery, VB, is equal to V1, which is the voltage of the first resistor, or the potential difference of the first resistor. V2 is for the second. V3 is for the third resistor. So V1 plus V2 plus V3 is the second equation. Whatever energy is being provided by the battery will be distributed between the resistors, or will be shared among the resistors. So this becomes our second equation. The third equation that we use is going to be the Ohm's law, which will be replaced, of course, after some proofs. Now, starting off with the second equation, we understand that voltages will be added together. So VB is equal to V1 plus V2 plus V3. Now then we replace this equation number 3 into each single component of this equation, right? We replace IR for everyone. So this becomes IB, the current by the battery. This becomes, you can say RT, the total resistance, equals to V1, represents I1 R1 plus I2 R2 plus I3 R3. Now, from this point onwards, we realize that the current was same, right? So based on, or you can say because of the equation number 1, current is going to get cancelled from all sides because it's the same. So IB cancels out with I1, I2, and I3, right? And we are left with the equation RT is equal to R1 plus R2 plus R3. That is the proof of series resistance, that all the resistances are added together. This is why they are added together. Moving on to the second part of the proof, which is the proof for the parallel resistor, right? Now, for parallel resistances, we are going to assume that, for example, this is our circuit, right? The circuit has a battery, right? And it has 3 resistors connected like this. This is, let's say, R1, this is R2, this is R3, and this is the voltage of the battery VB. So the current generated by the battery is going to be called IB, and this is the main battery current, which comes to this point and gets divided among 3 resistors. So this will be I1, this will be I2, and this will be I3. So starting off from the first point, the current is going to get divided. So current divides, which is going to be IB equals to I1 plus I2 plus I3, right? And the second part of the system that we already know is that the voltage remains same. Voltage is same, which means that the voltage of the battery is equal to V1, is equal to V2, is equal to V3. And of course, the third equation, the Ohm's law, which we are already familiar with, is V equals to IR. So moving on to the proof, we understand that we're going to use the equation number 1, carrying this one forward. So this is IB is equal to I1 plus I2 plus I3. Now let's replace a formatted version of V equals to IR in this equation, which is going to be V divided by R equals to I. Let's replace this into every single variable or representative over here in this equation. So this is going to become VB divided by RT, or total resistance, equals to V1 divided by R1 plus V2 divided by R2 plus V3 divided by R3. Now we understand that voltage is same for all the resistors. So by that equation, or you can say by that system, we can realize that voltage is going to get cancelled out from this equation, and we are going to be left with 1 over RT equals to 1 over R1 plus 1 over R2 plus 1 over R3. So again, the proof for parallel resistances is also shown or represented over here. Now, to represent these things in terms of circuit, let's move on to a circuit example. Now, this is a series circuit, right? We understand that we have 3 resistors in series to each other that are represented over here. Okay, so this is, let's say, R1, this is R2, and this is R3, right? Let's try to play this simulation. Let's see what happens. So we close the circuit and we realize that the current is flowing in the circuit. Let's measure the current of the battery. The current of the battery is 0.4 amperes. And if I go to any part of the circuit, you will realize that even if I measure the current after the resistor or before the resistor, the current remains same. This is why in the series proof, we represent, or we say that current is going to be the same. Now, if we move on to the voltages, for example, let's say that we place the voltmeter across this resistor. It is representing 2 volts. You can ignore the negative sign. If we swap the position of the voltmeter, it will give you the positive answer, but that's going to be difficult over here. That's why I'm sticking with the negative values. No need to worry about that. Moving on to the next part, if I measure the voltage of this resistor, this is going to come out as 2 volts. So this was 4 volts. This was consuming 2 volts. Let's write this down on the screen. So this is consuming 2 volts. This is consuming 4 volts. And let's check out what's the voltage of the third resistor. So the third resistor, across that resistor, we are getting 8 volts, right? Now, 8 volts. Now, when you add all of them together, 8 plus 4 plus 2, you will get 14 volts as your answer. And that's why we've been saying that voltage gets divided across the series combination. And whatever voltage of the battery is going to be there, it's going to get divided or shared between the resistances, right? Similarly, we move on to the second part of the system. Let me clear this out. Similarly, when we move to the second part of the system, that is this parallel voltage or the parallel circuit, we realize that voltage across all the resistors is going to be the same, even if the the resistances are different. Let's say that this is 5 ohms, okay? And let's say this is 20 ohms for the sake of example, okay? This is 20 ohms. Now we close the circuit and we realize that the current is flowing, right? When I measure the current of the battery, it comes out as 3.5 amperes, right? It is 3.5. When I measure the current in this branch, this is 0.5, this is 1 ampere, and this is 2 ampere. If you add all of these 3 together, you will get that the current is going to come out as 3.5 amperes, right? Which is the total current. This is what we've done in this proof, that the current provided by the battery is going to get divided into these 3 branches, right? And we also considered that the voltage is same. Now let's check if the voltage is same. We check the voltage of the battery, which is 10 volts. Now let's move on to the second resistor, which is 20 ohms. The voltage is 10 volts. Let's move on to the second resistor, 10 ohms. The voltage is still 10 volts. And over here, the voltage is still 10 volts. You can see that very clearly. Okay. So even in the simulation, we can see that the rules that we start with are actually being implemented. Okay. All right. So moving on to this question, let's see what happens. Okay. So in this question, he says that the 2 volts voltage is being supplied, and this is the circuit that looks like. The one thing that is confusing about this equation or this question is that he uses the letters and labels them as V1 and V2. So let's see where those voltmeters are connected. He says that the V1 is actually the voltage between S and P, which means that this voltmeter is connected like this. This is V1 like this, and V2 is connected, or you can say V2 is connected between S and Q. So it looks something like this, that this is where the voltmeter is connected, and the second term of the voltmeter is actually connected at this point. Now, one thing to realize about this system is this, that even if you had connected this at this point, it would still prove to be exactly the same system. Why? Because the voltage remains the same across the wire as well. You see, the voltage of the wire is actually 0. So it makes no difference. Okay. All right. Now, voltage of this 3 kilo ohms resistor is referred as V2, and the voltage of 5 kilo ohm resistor is referred as V1. We understand that both are connected in parallel combination, so the voltage across this combination is going to remain same. Let's say that this is also going to be 2 volts, and this is also going to be 2 volts. One trick, or you can say one shortcut that is straight away, is that voltage of this first branch does not need to be calculated. Why? Because the resistances are equal. When the resistances are equal, that means voltage is going to get divided equally. So I can say, or I can guess, that V1 is going to be equal to 1 volts. I understand that. Now, when we come to this point, we realize that the resistances are different. So I need to calculate the voltage. I can use the potential divider rule because they are connected in series. So that suggests that whatever voltage, whatever resistor's voltage I want to find out, keep that in the numerator, divide this with the total, which is 2 plus 3 of this branch. Multiply this with the voltage that you want to share, right? Which is this one. So this is 2. This comes out as 1.2 volts. Okay, fine. Which means that the reading of V2 is actually 1.2 volts. Okay. Now let's come back to the question. He says that the question is actually V1 minus V2. We understood that V1 was equal to 1.0 volts and V2 is equal to minus 1.2 volts. So if I subtract them based on the equation that he's given me, the answer comes out as negative 0.2 volts. The answer is going to be option C. As mentioned earlier in the simulation as well, it does not matter. No need to worry about the negative voltage. It is just a matter of swapping the terminals. If I keep this over here and I keep this over here and I close the switch, the voltage is positive. If I keep this over here and I keep this over here, the voltage will be negative, right? No need to worry about this. Okay. Moving on to this question. The reason to add this question, I understand this is an easier question, but the reason to add this is to show you how to do this on the calculator in one step. Okay. First, we need to realize that 20 and 8 are connected in series. Let's add them together. So let's call this branch P and let's call this Q. So the first branch that is on the top actually gives me 28 ohms by adding 20 plus 8. The second branch is 6 and 8, which means that if I add them together, this is going to be 14 ohms. The third branch is simply 7 ohms, which is connected like this. So 7 ohms. Now, ideally, what should be done is using the parallel formula, which is going to be 1 over 28 plus 1 over 14 plus 1 over 7. Now, when you do this, you forget that this is actually equal to 1 over R. You forget to take the reciprocal at the end. Now, to avoid this mistake, what you can do is you can put all these values on the calculator and raise it to negative 1. This will automatically take the reciprocal for you. Let me show you how it's done on the calculator. This is what you will get. This is what you will see on the calculator, or you can say this is what you should see on the calculator. Simply add your numbers in fraction, put a larger bracket, and then simply use this button as x raised to minus 1 or this power button and then raise to power with minus 1 adding digits. Now, when you press equals to, you will get this answer straight away. If you don't take the reciprocal, you will get your answer as 1/4, and you will mistakenly write 0.25 ohms as your answer, which is wrong. Be advised that you forget that you have to take the reciprocal at the end. 4 is the answer, not 0.25. Okay, so as I've shown you how to do this on the calculator, we can move on to the next question. These are the symbols that I was referring to before, that these are the symbols you should be familiar with. These are added in the syllabus and they are present on page number 54. So please go ahead, go to page number 54 and see what these symbols represent. Okay. All right. So this question, these lines are just basically added so that you can see that these questions are still being asked. Now he says symbol, what symbol this represents? This is an LDR. Okay. Part B. This is the symbol of a fuse. We know this from O levels, and of course it is similarly carried to A levels. Question number 35, he says, what changes with temperature? And we know that this is a thermistor, a resistor changing resistance based on temperature. Now, next part is based on internal resistance versus terminal potential difference. What is internal resistance? Where does it come from? Basically, when you look at any source, be that Wapta, be that cell, be that battery, be that anything, whatever source there is that you're using to produce or use electrical energy, it has some internal losses as well. If, let's say, you're talking about a lead-acid battery, then the chemicals have to move to their respective anode or cathode, and while they're doing so, they are experiencing resistance while they're moving through the solution, right? Or moving through the, you can say, the liquid paste of a solid state battery or a solid cell, right? Now, that calls for the resistance of the cell, right? Now, we need to include that in our calculations. In O levels, we don't do that, but in A levels, we need to include them. You're not required to generally find it out, but it's generally given. But even if you want to find it out, you can use the O levels method to find out the internal resistance as well. So we understand that internal resistance will be a part of every source, right? Be that a generator, be that a cell, be that battery, be that anything. Now, we need to include that in our calculations. So what happens? What is terminal potential difference? What is internal resistance? What are the total voltages, and what the terminology regarding A levels is going to be? So first, we need to realize that EMF is what the battery can do for you on a good day when there are no internal resistances. For example, this is what the manufacturer commits to you. That, let's say that a manufacturer says that the cell EMF is 2 volts. He's trying to tell you that chemically speaking, if everything goes well, if there is no internal resistance, this is what it can do for you. But as soon as you connect the circuit as soon as you connect the battery to a circuit, you realize that you are not getting 2 volts exactly, even if the resistor is single. Where is the extra voltage going? Where is the rest of the voltage going? So that voltage is being lost in the internal resistance or the internal resistance component, right? Now, when we include this current, then we realize that the energy or the EMF provided by the battery is being utilized by 2 components. The external resistor, which is going to be the potential difference as IR, and the internal resistance, which is going to be V equals to capital I small r. So the total equation basically looks like this, that the EMF of the battery, which is the energy provided to the electron, is being consumed by 2 elements, which is going to be V equals to IR plus IR with the small r, right? And if you take current as common, then this is going to become R plus R, which is going to be E equals to like this. Now, previously we realized in O levels that only the external resistor is the consumer. Now we have to include the internal resistance as a consumer as well in this equation. Okay, so now let's add these terminologies into this equation. So this is primarily your EMF, we understand that, and the voltage that is being used by the internal resistance is called lost volts because you didn't get them. So if you were to connect a voltmeter across this internal resistance, the voltage that you're going to get are going to be considered as lost volts. You are not going to get them. And if you connect a voltmeter on the resistor or the external load over here or over here or over here, these 3 locations is how he can confuse you. Okay, no need to worry about that. So these 3 voltages, whatever these voltmeters tell you collectively, right, as a single entity, right, these are all going to tell you the same voltages, be advised. Okay, this is called terminal potential difference. This is what you get on the outside. This is what you get from the cell at the end of the day. Once it has compensated for the internal resistances, whatever voltage is left out will be given to you to be utilized on the resistor on the outside. Let me give you an example. You can see that over here we have an external resistor, right, which is, let's say, 9.5 ohms, and there is an internal resistor of 9.5 ohms. Let's reduce its value to 0.5. Okay, they're generally very low in comparison to the loads. We have a battery of 10 volts, right? Let's play this and see what the current is. So the current is 1 ampere, right? If by any means the internal resistance were to increase, right? If it was to increase, then you can see that the current starts decreasing. Just like a series circuit, that if the total resistance increases, the current decreases, okay? Similarly, if it's low, right, the resistance remains low, and you start increasing the resistance of the load, of the external resistance, then the current starts decreasing again, right? There is no difference to the voltage of the EMF, but the current starts decreasing. Okay, but of course, according to the potential divider rule, if you increase the resistance, the voltage also increases. Okay, the share of the voltage of the resistance is going to increase by simply using this equation, which was Rx divided by R total multiplied by EMF, the potential divider rule. I'm sure we are familiar with that as well. Okay, all right. So this is what happens with the internal resistance. Okay, so I believe that we understand the term of terminal potential difference. We understand lost volts. We understand EMF as well. Okay. Moving on to the respective questions. We have this one. This is going to be actually based on algebra, so no need to worry about it. There is nothing special about the question. Only algebraic manipulation is what is difficult about this. He says, what's the power dissipated in the external resistor? A bunch of variables you see, no need to worry about it. Let's try to solve this by simple mathematics. Okay, you can solve this by the current method as well. You can solve this by voltage method as well, but voltage method proves to be a bit lengthy. You can try this for your own practice, your choice, okay? But right now I'm going to do this with the current method, okay? Let's move on. So we have E as our EMF, R as our internal resistance, and capital R as the external resistance. So the formula for power I'm using is I square R, because I'm doing this with the current method, okay? And then if I want to find out the current through the circuit, I can simply see V equals to IR. The voltage provided by the battery is E. The current is, I'm letting the current to be I. And the total resistance, because they're both connected in series, is going to be R plus small r, right? And I is equal to E divided by R plus R. Let's replace this current into this equation. So what are we left with? We are left with E divided by R plus small r whole square into capital R, which is this. So when you open this up, you realize that E is going to get squared, R is being multiplied, divided this with R plus R whole square. This very much looks familiar to option B, which is the answer. Okay. All right, you can try this with voltage method as well, the voltage divider rule. Find the voltage of this one, then subtract it from this one, and then use P is equal to V squared over R. You can try that as well. Okay, next question. So this question, you can pause the video and try this on your own, but let's try this question. So it says that these are identical cells, right? The first EMF is E, the second is also E, so they are identical. And they have internal resistances as R1 and R2. And they are connected in series, and the voltmeter, this is important piece of information, is 0 volts. Now, this voltmeter having 0 volt means that whatever voltage this resistor is consuming or is using up was also being provided by the battery. Of course, throughout the circuit, it could be the other way around. It's possible that some of the voltage is being used by this one, and this one. But voltmeter reading being 0 across these two terminals means that whatever energy was available at this terminal and whatever energy is available at this terminal, they're both equal. So whatever R1 used up, E had to provide it. Okay, we understand that voltmeter or voltage is energy, right? So let's start with the basic equation. So what does the equation look like? Okay, so I can understand and I can see that both cells are connected in series. So both voltages will be added together. So according to Kirchhoff's law, this will be E plus E, both voltages are working together in the similar fashion, equals to I into the total resistance, which is R plus R1 plus R2. Okay, and if I want to combine this together, this is going to look like this. 2E equals to I into capital R plus R1 plus R2. This is the first set of equation. The second information, or the second equation, comes from this information. We understand that across this loop, the voltage is 0. Whatever is being provided, it is being consumed. So I can see that E should have been equal to IR1, right? Whatever energy provided by the battery is being consumed by this resistor. So this is what the equation is going to look like, okay? So let's replace this equation into this part of the equation. So it's going to look like this. 2 times IR1 equals to I into R plus R1 plus R2. And we can very well see that this I is going to get cancelled out. So we are left with the 2R1 equals to R1 plus R2 plus capital R. Since he says what's the resistance of the external resistance R, I'm going to make this the subject of the formula and take everything on the other side. So this R1 subtracted with R1 is R1 minus R2, taking R2 over there becomes minus R2 equals to R. So this is going to be R1 minus R2.